Hey guys, welcome back. We're going to continue on our trek through the different states of matter. We've already covered solids, we've covered the atomic nature of matter. Today we're going to be talking about liquids. Solids are really interesting. They do some fascinating stuff. Liquids are also fascinating, and they do completely different kinds of things. Where they're similar to solids is that they're both fairly incompressible substances. Liquids are very difficult to compress. Solids are also very difficult to compress. When we get to gases, we'll find out that you can, in fact, very easily compress gases. So this is kind of where we see some similarities between liquids and solids, but not necessarily do we see them with gases. Now, where liquids do have similarities with gases is in the fact that they tend to change shape the same way that gases do. So in that way, both liquids and gases are similar, and in another way, liquids and solids are similar. So you can understand that there's reasons why these three different stages or states of matter exist to accommodate different physical factors. All right, so let's go ahead and start. This is obviously a water droplet coming in, and there's some interesting features here. Notice that the droplet comes out, it's not spraying all over, it's staying in a cohesive ball as it splashes up into the air. We'll get into why that occurs towards the end of this lecture. All right, so to understand some of the important and most fundamental aspects of liquids, you have to understand certain physical phenomena and certain criteria. Just like how we had to learn density and things like that in the previous lecture, we have to learn some of these features for liquids as well. So it turns out that for liquids, an important thing to be able to understand is pressure. And all pressure is the force per unit area that one object exerts on another. So an equation forms just pressure is equal to force over area. And so I have a picture of this is a glass of orange juice. When I was making this particular slideshow, I was really jonesing for some orange juice. Anyway, so here's some fresh orange juice. There's the oranges back here. And really the reason why this photo is in here is because the pressure up here at the top is going to be lower than the pressure down here at the bottom because you have a whole column of orange juice sitting on top of it. So obviously, the force per unit area at the bottom is going to be greater than it is up here at the top. And it also depends on area over which force is distributed. And here are the the units, newtons, meters per second squared, foot pounds squared, or something that I actually really like is pascals. And pascals is basically the equivalent of a newton meter squared. All right. So here's an application of how we can understand pressure. So as in terms of how things are distributed over areas. So here's a teacher lying on nails being completely unharmed. And the reason why is the force is applied over many nails, not a single nail. If there was just a single nail there and they sat on it, they'd be in deep trouble. But you combine the surface area of the nails all together and it results in a tolerable pressure that does not puncture the skin. Right? So if you took that apple and you dropped it on there, it'd go right in there. So this is an apple that's got a very low surface area relative to the amount of pressure that's put under it, and it goes right onto the nail, whereas this person's able to lay down on it. So right back to the pressure is equal to force over area. And the larger you can make that area, the lower that pressure is going to be. So pressure in a liquid is force per unit area that a liquid exerts on an object. And it's depth dependent. It's not volume dependent. So these two people here are different volumes. They're not going to be exactly the same size. But the one that's going to be exerting or feeling more pressure is going to be the one that's deeper in the water. So, for example, you swim twice as deep, then twice as much weight of water above you produces twice as much pressure. This is common sense. So the person who's taking this photograph is under considerably less pressure than these two divers are right here that are looks like they're diving on a coral reef. Another feature of pressure is that it acts equally in all directions, right? So it's not like when you're in the water, it's got a certain vector to it, right? It's not a true force, it's force over area. Pressure is a little bit different than what a genuine force is, which has got a real vector to it. So it's actually a scalar quantity. For example, your ears feel the same amount of pressure underwater no matter how you tip your head. You can go like this, you can go like this, and you'll still feel that pressure. Some of you can even feel it when you're going up over a hill. The air pressure around you will drop, and your ears will start to pop, and as you come back down, they'll pop again or whatever. You notice that just turning your head won't clear it out. The bottom of a boat is pushed upward by water pressure. So notice that here's basically all the different directions. But if you're at the surface here, that means that you don't have this down arrow. The only down arrow would be gravity. There's no water force above it. So the reason why a boat floats is because, or a beach ball would float, is because, these are the examples here, beach ball and a boat, which is why I'm using them. You're up here, there's no downward arrow working on you. There's only the ones on the sides which cancel each other and the one from down below. And we'll talk about this one down below. It's called buoyancy force in a few slides. Okay, so pressure is independent of the shape of the container. It doesn't really matter. Notice that this person has 4 different containers. There's a liquid in it, and notice the liquid goes to the same height all the way across. So it's the same pressure down here at the bottom. It doesn't matter what it's filling. All right. Same thing is going to be true here. If this valve here is open, the pressure that's in here is going to be the same as the pressure or the level of fluid in here, and the pressure is going to be the same at any equal distance below that high level here. In equation form, pressure is just something called, this is the letter, a Greek letter. So it looks like a P, but it's not. It's the letter rho. It's actually the Greek letter R. The letter R in Greek. In English, we've actually taken off most of this tail because it looks too much like the letter P when you do that. So anyway, it's P equals rho G, of course, being gravity, and then H, which is the height. Where pressure is, P is pressure, rho is density, and G is gravity, H is height. So density, we'll recall, was in our lecture on solids. So we're going to be using that a lot. So the effects of water pressure, it acts perpendicular to surfaces on a container. So if you put an object in here, the pressure always comes in perpendicular. It comes from the side. It's not coming in from some angle this way and this way. If it was to come in that way, it would be canceled. The only way that we actually see a pressure with a net exertion or measurable effect is in the perpendicular direction. So in this case, we'd have forces we'd have pressure surfaces in 3 different directions. All right. Liquid spurts at right angles from a hole in the surface. Why? Because it acts perpendicular to the surfaces of the container, right? So it's always going to come out at right angles. So notice those arrows, an arrow, and an arrow. But of course, the greater the depth, the greater the exiting speed, because it has a greater velocity, because it has a greater force that's accelerating it. So this is not going to go out as far. This will be greater. This will be the greatest. And a lot of first-year calculus, or a lot of first-year physics students that are taking calculus-based physics, one of the fun things they get to do is calculate what those velocities would be coming out of here using some really simple concepts. It's kind of a fun exercise. So something to look forward to, those of you that decide to get into physics, is fluid dynamics. All right, another really neat aspect of fluids is buoyancy. This doesn't happen with solids. It happens to a very low extent with air particles and with gases. But in liquids, it's a really big deal. And if it wasn't for buoyancy, we wouldn't have ships that float. We wouldn't have all kinds of the cool technologies that we have. And we've learned as human beings to be able to take advantage of a lot of these features. So, of course, what is buoyancy? Well, buoyancy is just simply the apparent loss of weight. It's not necessarily mass, right? Mass and weight aren't the same thing. It's the apparent loss of weight of a submerged object. And so, I don't know if you've never done this, you should do this experiment at home, or do your experiment next time you go to the beach or whatever. Take a rock, find a nice rock, big enough to hold in your hand, and submerge it in the water. And the moment you submerge it into the seawater, or if you happen to live near a river, submerge it in the river, you'll notice that the rock suddenly feels like it's a lot lighter. All right, it won't feel nearly as heavy. And the reason why is because of this buoyancy force. And that buoyancy force, the apparent loss of weight, I should say, is equal to the amount of the water that is displaced. So what do we mean by displacement? Well, it means that the amount of water that's pushed out of the way, if you weigh that water that comes off of that, it's equal to the force that is being subtracted off of the weight of that rock if you were to submerge it at the beach. I highly recommend that you do it. You'll really get a better understanding of buoyancy if you do this. All right, so I was talking about displacement and the displacement rule. let's go over that in a little detail. All right, we got a couple of slides on this to make sure we nail this well. So a completely submerged object always displaces a volume of liquid equal to its own volume, right? Always does. That's an important concept. Archimedes would take advantage of that later on. For example, place a stone in a container that is brimful of water, in other words, right to the top. And the amount of water overflows equals the volume of the stone. So you put this in here, the water overflows, you capture it, and the amount of water that is in here is equal to the volume, or the volume of water here is equal to the volume of the rock or the stone, right? Makes sense. We can do some really cool things with this, though. Of course, also don't forget the fact that the rock actually weighs less now that it's in the fluid as well. Okay, why is that the case? So buoyant force, or the buoyancy force, is a net upward force that a fluid exerts on an immersed object, which is, say, the weight of water displaced. Okay, we've been talking about that. The difference in the upward and downward forces acting on the submerged block is the same at any depth. So here we've got pressures, right? Two surfaces. Down here, it's going to be under greater pressure than it is going to be up here. But as you sink it down into a fluid column of, say, water, as it goes down, that difference is all that matters, right? The fact it's under greater pressure here and greater pressure here, it's still, the difference is only one of these arrows. Notice there's an arrow missing from here, there's an arrow missing from here, and it's an arrow missing from here. Whatever that arrow is worth, that's the amount of difference. And that is going to be representative of the upward force that's going to be pushing on the object. So it turns out the buoyancy force is equal no matter where you are in the water column. So that allows us to ask some questions. You know, is it going to sink or is it going to float? You got to ask this question with a submarine down in the lower left-hand corner. You know, this is a Typhoon class Soviet ballistic missile submarine. It's the largest submarine ever built. They're as large as tankers, actually. They're huge. I think there's only one left in the world that's actually still operating. But anyway, how do you get something that big to sink or float and to control it? Well, it's just as simple as a buoyancy argument. So objects sink when weight of the submerged object is greater than the buoyancy force. Makes sense, right? If the downward force is greater than the buoyancy force, you're gonna go down. Objects neither sink nor float when the weight of the submerged object is equal to buoyancy force, or the buoyant force. Object will remain at any level. So as long as the ship, for example, the submarine, as long as it's not crushed by the pressure, it'll remain at any level as long as the buoyancy or the buoyant force is neutralized. And this is called neutral buoyancy. And the way that submarines do that is by taking seawater into their tanks. And then when they're ready to actually surface, they blow the seawater back out. Why does that bring them to the surface? Well, objects float when the weight of the submerged object is less than the buoyant force it would have when submerged. When floating, the buoyant force equals the weight of the floating object. Okay, so that's the whole goal of a submarine. It's basically moving water in and increasing its weight. In doing so, it's balancing the buoyant force against its weight. If it happens to get too much water in, it will start to sink like a stone. If it, so it's a balancing act for a lot of these things. So now that kind of leads us into one of the most important things that we can get from fluids, which is Archimedes' Principle. Archimedes' Principle was discovered by a Greek scientist named Archimedes. He actually was a Spartan scientist, and we usually think of Greece as a single nation, but at the time it wasn't. There were city-states. He was a Spartan, and he did a lot of work with military hardware for the Spartan army. So he discovered several things such as Archimedes' Principle, but he also, a lot of people are now beginning to believe from ancient manuscripts, may have actually been somebody who discovered at least the beginning stages of calculus without actually just getting to the point of discovering it. That wouldn't come until Isaac Newton would come along much later. But Archimedes basically had discovered it. It was in his manuscripts, at least the ideas that would lead to calculus. And then he was killed in a battle. So that's kind of how that goes down. and then his learning was essentially lost for 1800 years. All right, so Archimedes' principle relates buoyancy to displaced fluid or displaced liquid. So it states that an immersed body, completely or partially, right? It doesn't matter. It could be floating or it could be under the water completely, is buoyed up by a force equal to the weight of the fluid it displaces. And of course, it applies to gases and liquids. So the buoyant force is equal to the weight of the fluid it displaces. This is kind of neat, not necessarily just the volume. What do we mean by that? So it doesn't mean you put it all the way down to the bottom here. We're just going to take a little weight here and demonstrate this. So the apparent weight of a submerged object, weight out of water versus the buoyant force. For example, here's a 7-pound block. So remember, pounds is a measure of force. It's not mass, it's force. So therefore it is a weight. The 7-pound block is submerged in water, apparently weighs 4 pounds. So we put it in the water. Before it's 7 pounds. We put it in the water, it's 4 pounds. A bunch of water spills out, of course, when you do that, because there's displacement. Then the buoyant force or weight of the water displaced is 3 pounds. So the difference between these two is 3 pounds, and sure enough, if you go and you measure the water that spills out, it's 3 pounds, right? So 3 pounds of force gives you 3 pounds of weight of water. That's kind of an interesting thing to put together. The actual volume wasn't put together or really worked out in this case, but we can work out the volume. We already know that it has to be equal one to the other, but the fact that we get a weight from it as well is really kind of interesting. That difference, 7 to 4, is 3 pounds. That's actually pretty profound. It's not something that you would just kind of expect. And so Archimedes is kind of a genius for figuring it out. So let's see how Archimedes' principle works. So in flotation, the principle of flotation is you have a floating object that displaces a weight of fluid equal to its own weight, right? So here we have something that's floating. There's a buoyant force that's coming up. There's the weight of iron. And as long as you're able to sink it down, right, and prevent the water from coming in and overwhelming this, it's able to drop in, and you are able to actually get a piece of iron to float. This is how battleships float. This is how aircraft carriers float. This is how tanker ships float and rowboats float, right? They're not made out of wood. They're made out of steel. And matter of fact, they can be made out of, in some cases, up to 100,000 tons of steel. Absolutely incredible. But in order to do that, you got to make sure that you build it so it goes down. It displaces a large amount of water to be able to improve the buoyant force. All right. So let's look at this example. A solid iron 1-ton block may displace 1/8 ton of water and sink. So it's displacing 1/8 of a ton. And because it's 1/8 of a ton of displacement, it's going to fall, right? Because there's 7/8 tons of force dropping it down. The same 1 ton of iron in a bowl shape displaces a greater volume of water, and that's therefore the greater buoyant force allows it to float, right? So you want to be able to do as much displacement as possible. If you're able to displace more than you actually weigh, you float. That's all there is to it. Another really cool application of some of the things we've been talking about here are the Falkirk wheel. Falkirk wheel is in Scotland, and it's actually a giant boat lift. So this is the wheel here. We're going to show a video of how it works here in a moment. But the Falkirk wheel's 2 caissons are brimful of water and the same weight, regardless of whether the boats are in them. So here we've got a boat up here on top, and there's a caisson down here, and here you can actually see both caissons better, which is why I put the second image in here. You can see the wheel is rotating. It's taking boats from this level up to here, and vice versa from here down here. There's a canal up here that this connects into. And as it makes the rotation, you have to ask yourself, is it lifting nothing but water on this side and nothing on that side? No, of course not. There's water on both sides. And so as a consequence, it turns out it doesn't take that much energy at all to rotate this thing. It only really just takes about enough energy to overcome friction. You're not doing a whole lot of lifting because the net force on the whole situation as this goes up and that goes down is balanced. So this is a really cool apparatus. And as far as I know, this is the only one of these in the world. So let's go ahead and watch this video. There's a YouTube video right here that kind of shows how this thing operates. And it's, like I said, people have remarked on how low the electric bills are here by taking advantage of these caissons. Of course, when a boat comes in, a boat just spills the water over, and the weight stays the same. It doesn't change. Okay, let's look at this.
The Falkirk wheel is a perfect example of functioning and modern architecture. Located in Scotland, it was designed to reconnect the Union Canal and the Forth and Clyde Canal. It serves as the only rotating boat lift in the world. The two canals had previously been joined by a fleet of locks, but in 1933, the locks had been dismantled. Officials had pondered what could be done to connect the two waterways. Hence the idea for the Falkirk wheel was born. Completed in 2002, the engineering marvel measures 35 meters tall. It took over 1,200 tons of steel to create, along with 1,000 construction crew members. Amazingly, the wheel only uses 1.5 kilowatts of electricity per hour to turn, powered by 10 hydraulic motors. The Falkirk wheel can carry at least 8 boats at one time, taking an hour to get from one canal to the other. Boat trips are offered so visitors can experience the Falkirk wheel. Not only is the wheel an impressive piece of machinery, it also serves as a major landmark in Scotland.
Cool. So anyways, you kind of get the idea. Really, really cool engineering marvel. Just basically taking advantage of Archimedes' principle, and it makes life kind of easy for these people. All right. So it turns out that Archimedes' principle, the way it works in water, is dependent on a couple of things. First off, that denser fluids will exert a greater buoyant force on a body than less dense fluids of the same volume. For example, a ship will float higher in salt water than in fresh water. The density of salt water is higher, 1.03 grams per cubic centimeter. Density of water, fresh water, is defined as 1 gram per centimeter cubed. So it will tend to float higher. And it makes sense, right? If you're going to be displacing more volume, that means you're going to be also displacing more mass, and more mass means more weight. Okay. And a useful equation to know to figure out that force that is being displaced is force equals volume times rho, which is density, times gravity. So don't worry about where I got this. Just assume that I got it from heaven. And for right now, we're going to just kind of put that in our back pocket. Archimedes' principle, of course, also applies in air. I'm not going to spend a whole lot of time talking about the air part of it because we'll be coming to that later on in the next lecture. But just really quickly, here we've got different pressures. Here's a higher pressure down below, a lower pressure up above. This is on a balloon. And then, of course, the two side pressures are basically just maintaining the shape because they cancel each other out. Anyways, the more air an object displaces, the greater the buoyancy force is. We've talked about that. An object displaces its weight, it hovers at a constant altitude. So as long as that arrow is equal to the weight of all these people in it, it'll hover at the same altitude. And of course, because it displaces less air, it starts to descend, it falls. Okay? Basically, the same principle that we've been using in water applies to the air as well. All right, so let's kind of review this. What makes an object float or sink, right? An object more dense than the fluid in which it is immersed will sink, in general. Number 2, an object less dense than the fluid in which it is immersed will float. And number 3, an object having a density equal to the density of the fluid in which it is immersed will neither sink nor float, will hover. All right? Basically, that's kind of the distilled synthesis of all of these processes we've been talking about since the beginning of the lecture. All right, so that leads us to a whole kind of new application of how liquids operate. Remember I was saying at the very beginning that liquids have a hard time compressing? They're very, very poor at compressing, and we can take advantage of this and do some really fascinating things. So a guy by the name of Pascal, which the unit of pressure is named after him. Remember I said earlier on that the standard unit or the scientific unit of pressure is the Pascal. It's named after this guy. So anyways, Pascal's principle was discovered by Blaise Pascal, a scientist and theologian in the 17th century. In the 17th century, a lot of people were both scientists and theologians. It was not uncommon for scientists to see themselves as mapping out God's creation. So that's kind of why you'll see those two together. Newton was the same way, no different. Basically, the principle states that a change in pressure at any point in an enclosed fluid at rest is transmitted undiminished. This is kind of neat, to all points in the fluid. And then, of course, it applies to all fluids, gases and liquids. The advantage in liquids is that liquids don't compress. It still gets transmitted in gases, but gases have a tendency to compress. And so we're going to spend our time talking about liquids specifically. And basically what it's saying is if you put a pressure here, or a force here on this piston, that force is being transmitted at all points throughout this entire fluid column, and you'll actually see that the force will eventually be, of course, exerted at the bottom of this piston and tend to want to raise it up. This is the foundational principle of hydraulics. All right, so let's see how hydraulics works in a hydraulic press. So here we've got a piston with 10 kilograms of mass on top of it, and it's over some area A, right? Remember, we're talking about mass over, in this case, mass over area. So the pressure applied to the left piston is transmitted to the right piston. So here's the right piston over here. It's this very large one. The area on this one is 50. So in this case, you can use a 10 kilogram load on a small piston to lift a 500 kilogram on a large piston. But the amount that it's going to move is going to be relatively small. But you get the idea. You can push here, and that force gets distributed over this entire area here. So the harder you push here, it'll actually give some piston movement here. Really neat. Okay, we see this principle used all the time, right? It's used in hydraulic devices in construction. Well, I'll actually show an example of one of those in something called an excavator here in a moment. It's used in auto lifts and auto stations. We've all seen our car precariously, those of you that especially have older cars that have been in the service station more than once, precariously positioned on top of one of these car lifts. Basically, there's an air compressor that pushes on the reservoir. The reservoir then exerts a pressure onto a piston, and the piston just lifts up the car. That's how it works. There's no physical solid beam here except for right on top, but all of that is being supported by a column of fluid, of hydraulic fluid. Okay, this is in fact exactly how this is an excavator here. You'll notice that there are these pistons right here. Here's a piston, here's a piston, here's a piston, and they're all connected through a series of hoses. See all those hoses right here? Those hoses are all connected to a central hydraulic tank and a series of pumps that are all connected right here in the middle. So this whole arm is operated entirely through a system of hydraulics. Okay, again, this is a big Caterpillar excavator. These are used for digging very deep trenches and are used in construction yards all across the world. But again, the main source of all of the hydraulics is right here. It's right in the center of the tractor. So another feature we need to talk about is surface tension. And we've all observed surface tension. The contractive tendency of the surface of liquids is due to surface tension. All right, so if there's examples that we can see. The one with the spring, this is actually out of a textbook that I use frequently. But the best example is actually the paintbrush or just a regular water brush. That when you put it into water, it spreads the bristles out. And then when you pull it back out of the water, it all pulls back in. And the reason why it pulls back in is because water sticks to itself. That's basically what surface tension is. It's the tendency of water molecules, because they're polar, to stick to one another. All right. Here's some examples of surface tension. You see these little beads everywhere? The surface of water sticking to itself prevents it from running down the spider web here. This is surface tension operating inside of a series of bubbles where you're actually able to use the bubble itself to make more bubbles within it, all of which have surface tension. All right. And the reason why it occurs is because of this phenomenon here. Remember, water is a polar molecule. It tends to have attractions in every single direction through these molecular attractions, a thing called hydrogen bonds. But when it's up here at the surface, right, we compare these two, notice that these three arrows that exist down below are not present up on top. So because they're not present up on top, that means that this arrow and this arrow and this arrow are all pulling down on the surface, and these are pulling apart through an attractive force, and of course there's something else pulling towards it, but there's nothing up above to balance it all out. So we have an imbalance in the kind of the field strength of the water. So these molecular attractions tend to pull the molecules from the surface into the liquid, and that causes surface tension. So this process up here compared to this one. So the missing 3 arrows right here is the cause of that. So there are several factors that will affect the degree of surface tension. There's the type of liquid. So water, it turns out, has a greater surface tension than oil. Oil is very low surface tension. Soapy water has lower surface tension than water without soap, because the soapy water tends to break up those bonds, so they're not as strong. And of course, the temperature of the liquid is also important. Turns out molecules in hot liquid have higher energy and are not bound as tightly as in a cooler liquid, right? They're bouncing around so much they don't have time to hold those bonds for long, and so it turns out it's not as strong. And that gives rise to something called capillarity. Capillarity is basically a manifestation of surface tension as it interacts with solids. So the rise of a liquid in a fine hollow tube or in a narrow space is called capillarity. We've all seen this. You've ever dropped water on the floor and seen it crawl up the wall or something like this, or crawl up into your carpets or something like this. That's basically capillarity that's soaking everything up from the bottom up. It's basically working against gravity. And it's simply an adhesion between the molecules of the glass and the water that draws the film of water into the tube. So here's the tube, and there's this cohesion that exists between them. Remember, there's no force. The surface tension is basically keeping this tight, but once it gets here, there's actually an upward force, and it takes advantage of it the moment that it gets that opportunity. And so the surface tension causes the film on the surface to contract. This raises the liquid from below to rise into the tube, which is what we're seeing here. It's pulling it up, right? So this is contracting, and that's going to rip it up. When the force of the surface tension balances out the weight of the liquid stops rising. So at some point, the force that is holding this thing tight is overcome by this column, but this column can only go so high. At some point, this and this are actually of equal kind of energy strength. That's kind of the best way you can think of it. The force is equal across that surface, even though the surface is not straight across. I hope that makes sense to you. Okay, so the height of rise depends on the weight of the liquid and the narrowness of the tube, right? So the easier it is to get access to the edges of that tube, and of course the weight of the weight of the liquid itself is going to have this direct effect, right? So we would expect the wider the tube, it's not going to be as effective as if it's quite narrow. In experiments, we see exactly that. So here we see this is some fluid, I believe it's water actually, but it's got a red dye in it. And you'll see that there's a wide tube, here's a narrow tube, and as they get thinner, unfortunately this one for some reason is not coming up all the way, but you'll see that the capillarity is actually working quite well right here. All right. So let's do a practice problem really quick to kind of get a better understanding of how, in this case, Archimedes' Principle is going to work. So our practice problem is an object that weighs 12 newtons is weighed underwater and found to weigh 4 newtons. Answer the following questions. Okay? What is the buoyancy force? Buoyancy force. That's actually pretty straightforward. We actually know that from the lecture. What is the buoyancy force? Buoyancy force is simply going to be, well, let's look at that. Let's do a drawing. Okay, so we have a liquid, and we've dropped some object in it. We don't know what the object's mass is or anything like that. We're just going to fill it in right here. Okay. We do know that on the surface, so this is our connecting line here. This is water. There. So the object weighs 12 newtons in air. But in the water, it's 4 newtons. And so we could actually just draw a diagram and figure out what the forces must be. So here's our object. Okay, here's our object. Put an arrow up this way and an up arrow going down that way. And we know that the net weight is 4 newtons. Well, we know that it's pulling down with 12 newtons. That didn't change. But the buoyant force is pulling it up in this direction. So that turns out that it's just simply 12 newtons minus 4 newtons, 8 newtons. So the buoyant force is equal to 8 newtons. You should have been able to see that in your head and kind of comment, right? It had to be the difference between those two. Okay. What's the second part of this question? Okay, now it's asking, what is the volume of water displaced by the object? Okay, the volume of water displaced by the object. Let's figure that out. We actually have a nice equation for that. I gave it to you a little bit earlier. The volume of water displaced by the object, the best equation to use to solve that is going to be this little equation that I told you fell from heaven. Go back and find it. There it is. Force equals volume. So here's volume. We know the force. We know the volume. We know what rho is, and we know what g is. The only thing we don't know is the volume. Cool. So it's going to be force equals v rho g. So let's start working through this. All right, so let's come back to this. So here we got force equals volume times rho times g. G, of course, is a vector that we know. All right, so the force is 4 newtons. The volume is our unknown. Rho we know, but we're basically gonna rearrange this equation. So let's go ahead and put that in this case, rho is water. We're gonna assume fresh water. 1,000 kilograms per meters cubed. If you don't remember where we came up with that, go back to the beginning of the lecture and you'll see that there. And gravity is going to be 10 meters per second squared. Cool. All right, so we can rewrite this in this way. Volume is going to equal 4. Now you notice that it's newtons. Remember what a newton is equal to? Newtons equal kilogram meters per second squared. All right, so we got 4 kilogram meters per second squared. And you can also write seconds squared as in the denominator by putting it as a -2. If you guys remember, that puts it underneath. So I'm just putting it like that to keep things nice and clean. It means the same thing that I wrote up above. And then down below is going to be 1,000 kilogram meters to the -3 times 10 meters second to the -2. All right, what can we do with this? What can we do with this? Well, the first thing that we can recognize right away is this really neat thing, right? Kilograms cancel out. Seconds cancel out. And that just leaves us with meters, meters, and meters. So we got meters to the -3 times meters, meters. All right? Okay, so we recognize here that we've got meters. I didn't write this very well. It almost looks like an exponent. I'll put it a little bigger. But this will cancel with that. And so basically, we now are left with this 4 times 10,000, or 4 divided by 10,000 meters to the -3. And when you do that math, you bring it up to the top, you get 4 1,000ths, or 4 10,000ths. So the 0.00, that's tens, hundreds, thousands. There's the 10,000ths. And whenever you have it in the denominator as a negative, you can bring it up to the top, meters cubed. So that's our volume. All right. So hopefully I didn't lose you in doing kind of the negative exponent stuff. This is something that you should have some experience with in your pre-algebra curriculum. Okay, so we're asked one more question. So we got 4/10,000 meters cubed is our volume. That may not seem like a very large volume, but you know it's something. You know, it's maybe the size of an apple. Okay, so we figured out the volume of the water displaced by the object is 4/10,000 meters cubed. What is the volume of the object? Hey, we know that too. The volume of the object is exactly the same. It's 4/10,000 meters cubed. That's Archimedes' principle. Okay, so I hope that this practice problem kind of helps clear things up for you as we go through liquids. There's some useful equations for when you're doing your problem sets. Pressure equals force divided by area. Of course, that equation I just used, the one that I told you fell from heaven, force equals volume times density times gravity. And then, of course, pressure equaling, this is one of the most famous equations in liquid dynamics, P equals rho GH, where pressure, density, gravity, and height are the variables in play. All right, so if you have any questions, as always, feel free to send me an email or to meet me on the message boards and ask any questions that you might have. Until next time, have a good one.